All right, one variable statistics part two. There's a lot to get through. I'm going to try and let the notes that are on the slides kind of talk for themselves. That way we can do more examples in the video, but we'll see what we get done. All right. This we already talked about in one variable statistics part one. This is just an overview of everything that we'll talk about. We already talked about measures of center and measures of variability. In this video, we got to talk about measures of position, including percentiles, quartiles, cumulative relative frequency, 1.5 IQR, and we're also going to talk about z-scores. I didn't write it there, but we're going to talk about z-scores there as well. And then we're going to talk about skew effects and how that affects the measures of center and measure of variability. Then we're going to talk about graphs and cubs. Remember, that's the acronym we use to remind ourselves how to describe distributions of data. We'll talk about quantitative as well as categorical data there. All right, first thing is measures of position, what a percentile is. Remember, the percentile is something that's got like a certain amount of data below it. So the 48th percentile has 48% of the data below it, which consequently means 52% of the data is above. The quartiles we talked about in one variable statistics part one, those are special percentiles. So Q3 is just the 75th percentile. And then Q1 is the 25th. Also, Q2 is the same thing as the median, is the same thing as the 50th percentile. Q2, 50% is below the data, the 50% of the data is below Q2, 50% of the data is above Q2. We've also got z-score. It's the number of standard deviations an observation is from the mean. So let me write this formula down. Z equals x minus mu over sigma. You'll have that formula one way or another on your AP Stats formula sheet. Can't remember exactly how they word it or how they write it, but it's something like that. I do want to point out z-scores are not only for normal distributions. We use z-scores quite frequently with normal distributions, but you can calculate a z-score for anything because all it is the number of standard deviations above or below the mean. That can apply to anything. All right, so outliers. Any observation more than 1.5 times the IQR from the nearest quartile. That sounds complicated. It's not. Bigger than this, smaller than this. That's all that is. We've done that rule before, and I'm sure you recall it now that you've seen it. Also, not as common of a definition, but it is a definition. If an observation is more than 2 standard deviations away from the mean, that is also considered an outlier, though it is not the one we typically use. Let's do some stats. Some descriptive statistics for a set of test scores are shown above. For this test, a certain student has a standardized score of z equals negative 1.2. We want to know what score this student actually received on this test. So if you remember from the previous slide, this is our formula for z-score. X is the observation, so that's what the certain student's score would have been on the test. So what we need to do is plug in what we know and algebra this out. So we're going to plug in the z-score of negative 1.2 that they gave us. X is what we're solving for. The mean is given in the data up here, or it's in the summary statistics, 1045.7. And the standard deviation is 221.9. So we're going to multiply both sides by 221.9. That's going to leave me with x minus 1045.7 on this side. And on the other side, that's going to give me a number that one might also call negative 266.28. Okay, and then from there, I just need to add 1045.7 to both sides. And when you do that, you get x equals 779.42. Make my decimal bigger. So AP Stats doesn't do a lot of algebra, but there was that little bit that sneaks its way in. All right. Oh, this girl looked like an FRQ, don't she? Ooh. Hi, FRQ. The summary statistics for the number of inches of rainfall in LA for 117 years, beginning in 1877, are shown below. A says, describe a procedure that uses these summary statistics to determine whether there are outliers. All right, well, that sounds like 1.5 IQR rule, right? So we're going to say any number greater than Q3 plus 1.5 IQR, or less than Q1 minus 1.5 IQR is an outlier. That's it. That's all you got to do. That is a procedure, isn't it? That would be how you would make that determination. That's all you got to write. B, are there outliers in these data? Justify your answer based on the procedure that you described in part A. All right, bet. So what I need to actually do is figure out what Q3 plus 1.5 IQR is. So Q3 is 19.250 plus 1.5 times IQR. Remember, that's Q3 minus Q1. So it's going to be 19.250 minus 9.680. And that number, when you put it into your calculator, is 33.605. Okay, so that's our upper bound. Any values greater than that would be considered an outlier. So let's go the other way. We're going to do 9.680 minus 1.5 IQR. And that turns out to be negative 4.675. So any number smaller than this one, any number bigger than this one. Well, they didn't give me the data. However, they did tell me two very important things. They said that the minimum is 4.850. Well, if the minimum is 4.850, this one's not going to give me anything, is it? They also tell me the maximum is 38.180. That number is bigger than this one, correct? So there's at least one outlier. There could be more. We don't know, right? Maybe 38 itself is in there somewhere, but there's at least one outlier because the maximum, right? So because 38.180 is greater than 33.605. I can guarantee there's one. There might be more. All right. The news media reported on the procedure, the news media reported that in a particular year there were only 10 inches of rainfall. Use the information provided to comment on this reported statement. Okay, so the underlined word only makes me think maybe the AP exam is trying to tell me, hey, they're exaggerating. They're exaggerating. Okay, so are they exaggerating? Is saying only 10 inches. Is 10 inches really that extreme? Well, we already know it's not an outlier, right? Because we figured that out. 10 inches is not an outlier. It's not an unusual piece of data. I think what's even more telling about this is look at the mean. 14.941. Now look at the standard deviation. 6.747. What that means is that 10 inches of rainfall is not even one standard deviation below the mean. So 10 inches of rainfall is not even one standard deviation below the mean. Okay, so now I've only kind of like half commented on what the news media reported, so I do want to actually input my thought that the news media seems to be exaggerating with the use of the word only. All right, there we go. That's FRQ. She's solved now. All right, let's do the next problem. Says data were collected on the amount in dollars that individual customers spent on dinner in an Italian restaurant. Which of the following statements must be true? Okay, so they gave us all the quartiles. So remember, Q1 is the 25th percentile. Q2 is the 50th. Q3 is the 75th. So 25% should be below 3627, 50% should be below 4427, and 75% should be below 5897. So which of these must be true? A, at least half of the customers spent less than or equal to 4427, and at least half spent greater than or equal to 4427. Yep. That's it. That's got to be the answer. Okay, bye. The weight of adult male grizzly bears living in the wild in the continental United States is approximately normally distributed with a mean of 500 pounds. So let's write that down. Let's say mu sub male equals 500. Sigma sub male is 50. For females, the mean is 300. And the standard deviation for females is 40. Approximately what would be the weight of a female grizzly bear with the same standardized score as a male grizzly bear with a weight of 530 pounds? So what we need to do is figure out what is the standardized score for the male grizzly bear, and then we'll use that to solve for the weight of the female bear. So Z equals 530 minus 500 over 50. So the numerator becomes 30. So Z equals 0.6 or 3/5, depending whether you like fractions or decimals. Okay, so now I'm going to use that to solve for the weight of a female grizzly bear that has a similar Z, has the same Z score. So I'll go 0.6 equals, don't know her weight, minus 300 over 40. So this is a lot like the problem that we did previously. Now, it just took us an extra step or two to get there. So I'm going to multiply both sides by 40, and I'm going to be lazy, not do this in my head as soon as my calculator scrolls down. Okay, 0.6 times 40, 24. I should have known that. Please don't be disappointed in me. And then I'll add 300 to both sides, and I get x equals 324 pounds. B. Cool. Finger guns, apparently. All right. Skew effects. So we got a little bit more notes. Remember, a skew always affects the mean and standard deviation. They're both super sensitive to outliers. Now I got a note there in case you forgot. Skewed right, tails to the right. Skewed left. Oh my God, no. Skewed left, the tail's on the left. Now it was really confusing that I drew them on the opposite sides of their names, right? Oh well. All right, the median and IQR, those are usually affected by outliers and skewness, but not very much. They're pretty resistant to outliers. It's not going to get a huge change. In general, though, the mean and median will be dragged into a skew, but the mean will get dragged so much further because it's sensitive to outliers. Great. Graphs. So these are the major types of graphs that we're going to deal with. With categorical data, it's just going to be a frequency table, which you've seen frequency tables forever. A bar graph, a segmented bar graph, which is usually used with relative frequencies, or a pie chart. I want to point out these two right here. These are often used for parts of a whole. All right, the major quantitative graphs that we're going to look at are histograms, dot plots, box plots, and stem plots. I want you to be careful about box plots because they like to ask a lot of conceptual questions about them. If I'm looking at two box plots and they have the same width for their box, that doesn't mean they have the same number of observations. You can't compare. You can counts. I knew it was in there somewhere. You can only compare proportions, right? I know 25% of the data is in this one spot. I can't say that that has more than one other of them. So maybe my words were confusing just now, but I hope that you understand what I'm saying. All right, describing distributions. So categorical data, there's really no trick. Just make sure that you're commenting on overall patterns. Notice when things are, which one's got the biggest one, which one has the smallest number of observations. Is there any trend at all? So no real trick. Quantitative data though, CUVs. Center unusual features, variability, and shape. Make sure that you're allowing yourself flexibility by using words like approximately. And if you are asked to compare, you had better compare. You have to use words like while, or is greater than, or is less than, something like that to show you're actually comparing and not just listing. All right, time to do some problems. Maybe. Okay, there we go. The histogram above shows the number of minutes needed by 45 students to finish playing a computer game. Which of the following statements is correct? The distribution is skewed to the right. No, the tail's not on the right. The distribution is skewed to the left. I'd buy that. The distribution appears to be normal. No, not at all. The distribution appears to be chi-square. Chi-square looks like that. And also goes out to infinity, so it's not going to be chi-square. The distribution appears to be uniform. No, those bars aren't even kind of alike. So, like we thought, it's this one. I don't know why I'm coloring it. You can enjoy watching me color it. Okay, great. A botanist is studying the petal lengths measured in millimeters of two species of lilies. The box plot above illustrates the distribution of petal lengths from two samples of equal size. Ooh, that's important. The two samples of equal size. That means I can compare counts. That's very important. Usually we can't compare counts, but since I know the sample sizes were the same, I can compare counts. It says one from species A and the other from species B. Based on these box plots, which of the following is a correct conclusion? The interquartile range are the same. Well, the interquartile range is the width of the box. I think it's pretty obvious they're not the same. The range for species B is greater than the range for species A. Remember, box plots start at the minimum, stop at the maximum. I think it's pretty clear these start and stop at the same spot. There are more petal lengths that are greater than 70 millimeters for species A than there are for species B. Okay, so 70 is like right here. So species B has at least 25% that are greater than 70. Species A does not have that same amount, right? So B should have more that are greater than 70 millimeters, which is not what that says. So that's wrong. So let me get rid of this so that we can draw on this again in a second, but that's wrong. There are more petal lengths that are greater than 40 millimeters for species B than there are for species A. Okay, so let's find 40 millimeters. All right, same kind of idea, right? Based on where the median is, I know at least half of the petals in species A are at least 40 millimeters. However, in B, look, the median's all the way down here. That means I can't guarantee 50%. So A should have more greater than 40. Which I guess, by elimination, here we are at the right answer, right? But let's look at it. There are more petal lengths that are less than 30 for species B than there are for A. Here's 30. About 25% in A, and more than 50% in B, because look at the median. So that's right. Great. All right, Robin works as a server in a small restaurant where she can earn a tip, extra money, from each customer she serves. The histogram below shows the distribution of her 60 tips from one day of work. Write a few sentences to describe the distribution of tip amounts for the day shown. This data is quantitative. I am going to use CUVs. The data is centered at... Now, I don't know what the mean of this is. I could estimate where the median is, though, right? Because the median should be somewhere around the 30th observation, since there are 60. So that leads me to think I'm somewhere in here, right? Because the 30th observation should be in there. Centered at, let's not say at, let's say between. So the data is centered between $2.50 and $5. Now, I don't know what the center actually is, but I know it's somewhere between $2.50 and $5, which that's going to come in handy in this next thing when I talk about, well, I guess I'm talking about unusual features next. So unusual features, that would include this gap. So there's a gap from 15 to 20. So there's my unusual features. Now I need to talk about variability. Now a lot of people like to say that the range of this data is 20. That's not necessarily true. The smallest smallest value possible is 0. The biggest value possible is 2250. That doesn't mean that the smallest value is 0. That doesn't mean the biggest value is 2250. So we need to give ourselves flexibility. So we're going to say the range is at most 2250. Now I need to talk about shape, skewed right. The distribution of tips is skewed right. Got lots of context. I was talking about the money, so putting the units helps with that. And then I talked about the distribution of tips. All right, this video is getting long. Let's try and wrap things up. One of the tip amounts was $8. Okay, so one of the tip amounts was somewhere in here. If the $8 tip had been $18, what effect would the increase have had on the following statistics? Justify your answer. All right, let's talk about the mean. If I increase the total amount, if I increase a tip by $10, the way the mean is calculated is by adding up all the observations and dividing by how many there are. So that means the mean would increase because the total amount of tips increases. Or total amount of the tips. The median. So we talked about this on the previous slide. The median was somewhere in here, right? Well, if I move an observation that's above the mean to a different spot above the median, sorry, if I move an observation above the median to a different spot above the median's not going to change. The physical center is still going to be there. So we're going to say will not change because both 8 and 18 are above the median. All right, that's the last slide. I'm not making this video any longer. Goodbye.